So in the last two examples, we looked at solids that were generated by rotating around horizontal axes of rotation. Now we're going to consider the disk method with a vertical axis of rotation. As we're going to see with this example, what this is going to have us do is kind of change how we view the disk method in terms of rather being a function of x with bounds in terms of x, we need to think about it as a function of y with bounds in terms of y. And I think that'll be apparent once we get a visualization going. So let's get started with this first example. And as we did with the other examples, I think it's always helpful to get a little bit of a sketch going first. So we've got the region bound by x is equal to the square root of 5 times y squared. Essentially, this is going to be a parabola, except rather than it being the function of x up along the or symmetric across the y-axis, it's going to be a function of y symmetric across the x-axis. So it's going to end up looking something like this. So we've got our y-axis, we've got our x-axis. So here we've got y, and in this case x is going to be a function of y. So we've literally tipped our world over 90 degrees here. So this curve, the root of 5y squared, is going to look like a parabola that's essentially been tipped over. So it's still centered at the origin. It's just in a slightly different direction. So this is the curve x equals the square root of 5 times y squared. All right, now we've said that this is bound between the x-axis or the y-axis and then the lines y equal -1 and y equals +1. So let's put y equals -1 and then y equals +1. And if we were to draw these lines in, so these are just horizontal lines, y equals +1, y equals -1. And we are going to rotate this about the y-axis right here. All right, so let's fill in the region that we're working with here. So this is going to be this top piece right here, and then this bottom region right here. And since parabolas are symmetric across their vertex, it may not look like it the way that I drew it, but these two regions will be the same because they are in fact symmetric, and that's going to help us out a little bit later on. All right, so there's our region. We know where we're going to rotate it. Now we also want to make sure that we draw our cross section. Now in this case, the cross section is going to be, again, perpendicular to the axis of rotation if we're going to do a disk method. So I'm just going to pick a random y value right here and draw a cross section. And if you use your imagination, we could think that if we took this cross section and rotated around the y-axis, we would generate a disk that's stacked along the y-axis, and we'd have a series of them all over to then get our full volume. So that's essentially what we're doing here. All right, so let's go ahead and we're going to set up our bounds next. We've got our sketch, we've got our cross section. Now we're going to get our bounds. Now since this is a function of y, along the y-axis, these are going to be in terms of y, because what we're doing is we're trying to think, where along the axis of rotation are we going to be stacking these disks? Well, they're going to start down here at -1, and we're going to stack them all the way up to +1. So here our bounds are going to be from y equals -1 to y equals +1. We'll take a note of that. So this is the region along the axis of rotation that we're going to be stacking all of these disks to get our volume. once we've got our bounds, we then need to get our radius. Now, in this case, the radius is also going to be in terms of y. So once again, we kind of go in and we think about what the radius is. And as we've mentioned before, sorry for the zooming in, but the radius is going to be the distance from the axis of rotation to a point on the boundary curve. So in this particular case, this distance from the axis of rotation to that point on the boundary curve is in fact just that distance under the curve, or the square root of 5y squared. So once again, we have a pretty nice one. In these cases where the axis of rotation is literally just the x-axis or the y-axis, these tend to lend themselves to more simple radii for the disk method. So this is just going to be the square root of 5 times y squared. All right, so now we're going to go ahead and we're going to set up our volume. So the volume is going to be equal to the integral from -1 to +1 pi times our radius squared, and we integrate with respect to y. Now we could integrate this and we would get our correct answer, or we could, in this case, maybe make our lives a little bit easier. Since we had mentioned that this is a symmetric curve about the origin, excuse me, about the x-axis, we could use that and say, well, what if I was just to calculate the integral from 0 to +1 of pi times the square root of 5y squared, and then double it. So essentially we're calculating this top area and we're multiplying it by 2. And that gives us our full area. I'm going to go ahead and I'm going to, just because 0 is so nice to work with the definite integral, I'm going to go ahead and I'm going to use this one. So again, I'll pull that pi out. So that's going to give us 2 pi times the integral from 0 to 1. And if we square out this root 5y squared, that's just going to give us 5 times y to the power of 4 dy. And if we integrate that, we're going to get 2 pi times 5 over 5, which is going to be 1 times y to the 5th. Evaluate that from 0 to 1. We're going to have 1 to the power of 5 minus 0 to the power of 5. And we're going to find out that our answer just ends up being 2 pi times 1. And then that would be the volume of that solid. Again, you would have gotten the exact same thing if you had started with the original, but this way might have been a little bit easier.